All right. Got that, pretty good. That's where we're at. Does that say paired? Or related or something? Related? Okay, here's where we're at. 2 weeks before spring break, we learned all about independent samples coming from independent populations, but we had the population standard deviations. That was the first one. Then the week before spring break, it was all about independent populations, independent samples, but we were given the sample standard deviations, and there were 2 equations related to that. So those are what we've covered so far on this quiz 3. Today, this week is all about means related to each other. How do you recognize these? You're gonna read a problem. By the way, I can't remember if it's Thursday or Tuesday next week, or Monday next week, one or the other. I have some problems ready to read to you to tell me which one it is. You're gonna tell me, because that's what needs to be done on this next quiz, is you need to be able to recognize which one of these equations to use. How to recognize this week's? It's all about, you're gonna hear a description where the samples are coming from the exact same population. And in most cases, it's the exact same sample before and after something took place. That's the most common. And I want to tell you why this is a big deal this week, is because, I know this is going to be hard to believe for some of you, but believe it or not, some of you are going on to your master's. I know you're going, oh, no way, I hate school, why would I go on to my master's? Because you're going to go to your employer, and your employer's going to go, hey, we'd like for you to maybe consider getting a master's. We'll pay for it. And that's the moment you got to go, okay, I have to get my master's. When they're gonna pay for it, you've gotta get it. And the most common, here's the deal with the masters. You got like maybe 12, 14 classes, and they're easier than your undergrad classes. Did everybody hear that part? They're easier. They're easier than this class. All your grad classes are easier than this class. But almost all the grad programs have a thesis. And that thesis is where you gotta prove you're doing research. And I don't mean a research paper like you're writing for an English class. You gotta do that kind of a research paper, but on top of it, collect data somehow and apply statistics to that data to determine whether there's your null hypothesis gets rejected or not. That is what a master's thesis is about, and a doctoral dissertation, if you ever decide you wanna go on past a master's. So that's why this is so important, because many people find this to be one of the easiest ones to write a master's thesis about. And so you find this to be a very common one. So if you get this week's lecture, you know you could easily do a master's if you're willing to put in the time and effort to write that thesis. I want to tell you what I hate writing papers. I hate it. The best part of my master's thesis was the data collection, because that's my particular, I find that easy. Writing the history behind whatever it was I was writing about. Turned out to be something like 63 or 75 pages or something like that. So your master's thesis isn't just some easy, like a homework assignment that's gonna take an hour. It takes a long time to do, and you have to reference everything you've read that you're referring to about the subject in which you're doing this research project on. Now let me give you an example. A friend of mine asked me to help him get his master's, write his master's thesis. And I said, you know what, to make it fun for yourself, relate it to something you're interested in. And he's a basketball fanatic, NBA fanatic. So he decided to write his on NBA players who are about to face free agency. I want to make sure everybody understands what that means. It's where a basketball player could go play for any team they want. The highest bidder will get them. It's called going to free agency. And so his assumption was, he's trying to prove that basketball players will play a lot harder the season before they're about to go to free agency, and he went ahead and collected statistics on players before they're going to free agency, right the year before they're going to free agency, to show that their stats are much better, and then after they go to a new team, compared to those stats, that shows it goes back to normal again because they got the big contract now, they can relax and they're more focused on making sure they don't get hurt. That was his whole thesis about. And he got his master's. So you can relate it to anything you want to, whatever you're trying to prove, whatever the theory is. And you can relate it to something you're interested in, so that way it doesn't seem like torture like mine was. So, let me read you an example problem. Look at the wording involved, how you can determine that it's one of these related samples. Sometimes called matched samples, sometimes called, I can't think of the other word, I'll think of it in a minute.
Paired.
Huh?
Paired.
Paired, thank you, that's the other word. Thank you.
Are you going to use them interchangeably, or is there one word that you're going to say?
I can't remember. I think I always refer, I don't know if I refer to them at all. You have to refer to them when you discover what it is. I'm not gonna give away whether they're master pair. But here's an example of what is master pair. Now remember, here's the definition in a way. The two samples are coming from the same population, that somehow they're related to each other, and in most cases, it's really the same sample before and after something took place. And here we go, ready? A manager is interested in improving productivity, and this is a poor worded one, by the way. It shouldn't be. It should be to see if productivity changes. I'm going to reword it. A manager is interested to see if productivity changes at a plant by changing the layout of a workstation. So there's some assembly taking place, probably involves several people, and they're thinking about changing the way it's laid out to see if it changes the amount of time it takes to make that item or assemble that item, whatever it may be. So it says, for each of 10 workers, now try to picture this. This is how the data is collected. For each of 10 workers, she measures the time it takes to complete the task before the change of the workstation, the layout, and again after the change of the layout. So collecting data before of 10 workers, collecting data after 10 workers. Here's the deal. It's the exact same 10 workers. That's what makes it paired or matched or related. It's coming from the same population. It's almost the same sample. And this is the most common way it's used, right here. My friend who did the basketball players, it was the exact same 30 basketball players. It was their stats before going free agency, their stats the season of free agency and after free agency, to compare them, two different parts, before and then free agency against after free agency. And since they're related, the same exact basketball players or the same 10 workers, that's how you recognize it. Anyway, that's how I wanted to start this off, is how to recognize the related and how common it is, really. So now, what do I want to do? Here's the deal. Let me get to it. There are two equations, just like all the other ones. There's, if you have the population standard deviation, let me show you that equation right there. You would do Z. I want you to write yourself a note. Slide 26 will not be on quiz 3 or the final exam. I'm right now calling it an audible. I'm decreasing the course load. I'm reducing it. All we're going to focus on is if you have sample standard deviation, which is the most common one. And if you're writing your master's thesis, it's probably going to be the case. You're going to use your sample standard deviation of the difference. So you're not going to be using Z, you're going to be using T. So we're going to skip Z. It's just like T, except for you got the population standard deviations, just like all the other formulas where you had the population standard deviation. We're focusing on slide 29. Slide 29 will for sure be on your quiz 3 and maybe your final exam. Everybody hear that? This is if you're given the sample standard deviation, because you're doing T. But the formula is the exact same formula. Now, another thing I want to point out. Since quiz 2, we've been doing this 2 sample hypothesis testing. And I've been telling you to ignore that right-hand side, that numerator, because it will always be 0 for this class. Same thing here. Ignore that right-hand side and the numerator here. It will always be 0. Anything minus 0 is itself, so you might as well just take that right out of the equation. And I wrote it up here in words as if that's not there. The mean difference, let me explain what mean difference is. It's not mean 1 minus mean 2, like we've had in the previous equations. Let me show you what happens in this one. In this one, you're taking every sample and subtracting the before, or in this case, it's after minus before. And you're doing each one. You're not finding the mean and then taking the mean of one minus the mean of other. You got to subtract every single piece of data that are matched, each pair. And you subtract those, and then you find the mean of all those subtractions. That's called the mean difference. So, let me write in a hypothesis here. Here it is. Tell me what that symbol stands for, H sub O. Not all at once, we are recording. And they can't hear you on that recording if you're all speaking at the same time. Yes, null hypothesis. There we go. Null hypothesis. And I'm going to put mean D, or you could write the word mean difference. and then it's either equals 0, or it's less than equal to 0, or it's greater than equal to 0. But the point I'm trying to make is, mean 1 minus mean 2 is not valid in this one. I might accept it though. I might accept it anyway, I don't know. But the point I'm trying to make is, in reality is, this is called the mean difference, is the left-hand side. So, let me go back to the formula now. All right, so the formula is the mean difference over the standard deviation of the difference, which you're about to learn how to calculate, divided by the square root of the sample size. Let me define sample size. Yes, there's 10 employees and measured, and then the same 10 employees measured again, that's 20 pieces of data. No, the sample size is how many pairs, which would be 10. Or in this case, I think there's only 6 employees in the example we're about to look at. It's how many pairs, not how many pieces of data, because you have a piece of data for the employee or whatever the thing is before, and you have a piece of data after. So you have twice as much data, but it's how many pairs you have. In this case, that problem, that example I read would be 10, because we use 10 workers. So the mean difference divided by the standard deviation of the difference, which you're about to learn how to calculate. This is the sample standard deviation of the difference. I forgot. Let me put the word sample there. If it's Z, it would be the population standard deviation of the difference. But we're using sample standard deviation. It's the only difference. We're skipping the Z because there's only one little difference right there. We're focused on the T because this is the most common one used. Now this is the critical, confidence interval. The mean difference, just like over here, plus or minus the critical T times that sample, let me add sample, that sample standard deviation of the difference over the square root of the sample size. You're basically the same way we do confidence interval, it's just that now the mean difference is the first character, the first variable. All right, now, how do we find that mean difference? How do we find that standard deviation of the difference? This is it. Here's the example. All right, and this is a good example because you're a manager. I know some of you are going, yeah, you're going to be managers, and some of you will even eventually be at big companies, and you're going to go, oh, I've got 100 employees. Oh my God, you got 100 employees. That's 100 headaches. And you're managing the employees, and you're going, I want them to go through this training, and you're talking to your supervisor, and you're asking for, it's going to cost with it's out of town, so with expenses and meals and hotel and the conference fee, you're looking at least $1,000 per person. So you're asking for about $100,000 to send these 100 employees. And your boss says, wait a minute, how do we know this is going to work? What is the purpose of this? And you're saying the purpose is that they're going to learn how to be better customer service, to have less customer complaints. And you're saying, look, I've been measuring customer complaints now for several years, so I know exactly how many on average per week or per month customer complaints our employees have. And so they say, okay, how about this? Randomly select how many there? 5 of them. Randomly, that's the key, by the way, for this to work. Has to be random. You can't say, oh, I know this one will improve and this one will to make you look good. Has to be randomly. Out of the 100 employees, every employee has to have a chance to be one of the random 5 in this case. And you have those 5, you pay $5,000, you have those 5 go to that conference, go to that training, and then they come back and they do their job, and meanwhile you're measuring complaints again after they've been back a while. What's their average per week? How many complaints per week are they getting? And here's before they went through the training, and there's after the training. And if there's a significant difference in the number of complaints, you've proven that the seminar trainings had an effect. But if the difference is just slight and not big enough, and it could be randomness that caused that difference. They had nothing, maybe the seminar did, maybe it didn't. You didn't prove anything. And on top of all this, I believe that your manager is asking you to use 1% significance, meaning you got to prove without a shadow of a doubt that this conference, this training at $1,000 a person is truly going to decrease the amount of complaints. Everybody with me? So here's the column. I want you to first talk about that after column. Look at the after. That's how many complaints after they had the training. And then, in this particular case, it's taking the after minus the before. Now, I want you to be careful. In most problems, it's whatever's talked about first minus whatever's talked about later. So you gotta be careful. You don't know what direction it is. And when you write your null and alternative hypothesis, it's all about what direction is that subtraction gonna take place. By taking the after, and I want you to think about this, for this training to take place, the employees would have to have less complaints after they came back from the training for you to prove this training worked. And you look at the numbers, the first employee went from 6 to 4. Hey, it kind of looks like it may have worked, but that may have been randomness that took place, not the training. But the second one went from 20 to 6. Again, we're not sure yet if it proved it, but that's a pretty big decrease. The third one went from 3 to 2, and 0 to 0, and 4 to 0. Now look at the 0 to 0. You're going, oh, why did we select that? Because it's randomly selected. You're asking for all the employees to go to this, whether they need it or not. So the random selection of the sample had to be any employees, including the ones who didn't need it. So that's why we have a 0 to 0. But it's the after minus the before, so you're gonna have a smaller number in most cases, minus the bigger number. The result, the difference will be negative. Negative 2, negative 14, negative 1, 0, and negative 4. You add up this column of the differences, you take it and divide by the number of pairs, your sample size. Now I know it looks like we have 10 pieces of data there, but it's 5 pairs, so we're only dividing by 5. Negative 21 divided by 5, the sum of the differences, that's what that stands for, sum of differences, divided by the sample size, or number of pairs, which is 5. Here is our mean difference. There's our first number right there. Where's that pen? Way down here, or is that just there? It is. Here's, if I were figuring out my test statistic, negative 4.2? There it is. There's that part, divided by. Now, here's the hard part. Define the standard deviation of the difference. You gotta take this negative 4.2, the mean difference, and subtract it from every difference you calculated. Let me repeat that. Negative 2 minus negative 4.2. So think about that. You're subtracting a negative 4.2. That's the same as adding. The two negatives are basically going to cancel each other out. So you have negative 2 plus 4.2. Negative 14 minus negative 4.2 would be negative 14 plus 4.2. So I did each of these calculations and I posted it. Look for the picture that's called, it's called slide 32, Business Statistics, Chapter 10-11, Calculation for Sample Standard Deviation. Negative 2 minus 4.2, negative 14 minus negative 4.2, negative 1 minus negative 4.2, and so on and so on. The formula, let me show you again. Whoop, whoop, whoop. Formula then says, after you subtract the mean from each one, square that answer. Then after you square each one, add those squares up, the sum of. So let's take it one step at a time. I went ahead and took negative 2 minus negative 4.2. Whatever that result was, I then squared it, and I got 4.84. I took negative 14 minus negative 4.2, and I squared it, and got 96.04. And I did that with each one. The next step is to add those squares. 128.8. Now look, here's the formula. You take the sum of all the squares, and you divide it by the number of pairs minus 1. This is your degrees of freedom for related samples. It's the number of pairs minus 1 is your degrees of freedom. Let me repeat that. For when you have matched samples, coming from the same population, paired, whatever you want to call them, related, the degrees of freedom is the number of pairs minus 1s. And that's what you divide by. You take the sum of all these squares, 128.8, divide by n minus 1, which was 5 employees minus 1 means we're dividing by 4. We get 32.2. That's your variance of the differences. There's your variance of the differences. But we need the standard deviation, so we got to square root it, 5.67. Let me go back to the slide. That's where that 5.67 comes from. Square rooting that variance. Everybody see that? I want to make sure you see that. This is posted. And it's, the title on it says, this is slide 32, the work on how to get to that 5.67. And you need to know this. Now you could easily set this up in Excel if you want to. but you need to know it. So now that we got 5.67, here I go. 5.67 over the square root of 5, because there were 5 pairs. There were 5 employees that we randomly sent to that training. There's how you calculate your test statistic right there. The mean difference that we calculated over that standard deviation of the differences we just calculated divided by the square root of how many pairs. Here's our test statistic, negative 4.2. Look how it says -0. We're just dropping that -0 off. It's always going to be -0. Over 5.67 divided by the square root of 5, negative 1.66. So this equals negative 1.66. Now let's find our critical value. Look at what they got for a critical value. Plus and minus 4.604. Is this a one-tail or two-tail? Look up in this box. Two-tail it is. Two-tail it is. Look how it's written. Mean difference equals 0. Mean difference not equal to 0. We're trying to prove that the difference from before and after for these employees are not equal to 0, that there was a real difference there because the training had an effect on them. But here we go. The critical, help me out. You know what? I didn't open my Excel page. Where's that? That's from week 5. I tell you what, I'd have this Excel. Don't forget. I shouldn't have put it on this sheet, but here it is. Where's my Excels? There's all my Excels. Which one are we using to find the critical value for these matched pairs, these related samples? Which one am I using? TINV equals TINV. Now look at the rule. It says use significance, degrees of freedom, but if it's one tail, double your significance. Let's go back to the problem. It's two tail, so we don't double the significance, and the significance is 1%. So here we go, 0.01 comma, and was it degrees of freedom? Degrees of freedom, what's the degrees of freedom? How many? 4 it is. 5 pairs minus 1, very good. And this is how you get 4.604. Now, plus, I forgot to put plus minus. Plus minus 4.604. Look at the number line. Here's positive 4.604. Here's negative 4.604. Here's our test statistic, negative 1.66, landing between the two critical values. Therefore, we cannot reject the null hypothesis. Cannot reject it. We did not prove at 1% significance that this training, without a doubt, caused there to be less complaints. We didn't prove it. We're not getting the other $95,000 for the other 95 employees. That's how it works. Look, we just wrote a master's thesis. How great was that? Let's use critical or confidence interval now. Is that on here?
Why'd you put,
No, it's not. Huh?
I was gonna say, why'd you put plus or minus if that wasn't a confidence interval approach?
Just so your critical value, just so every time I do critical value, I always put both plus minus, just because I want to check and see if my test statistic lands between them or not. So I always use plus minus when I'm calculating my critical value. Let's do this confidence interval. Here we go. Let's set this up. Here's where all the points are, is in the setup, if you're asked to use this approach. Negative 4.2 plus and minus my critical T, there it is, 4.604 times, parenthesis, my standard deviation of the difference, 5.67 over the square root of the sample. We have 5 pairs. There's the setup. Everybody see how I set up that confidence interval? There's where all the points are. Did I calculate the confidence interval? I think I did. Where is it? I think I did it on here. What slide are we on? Slide 33. I have something here. Slide 33, let's see. 59, 11, 10, 11, slide 33. Confidence interval, there it is. There it is. Let me make it bigger. Negative 4.2 plus and minus 4.604 times 5.67 over the square root of 5. You do all the math on that. I want you to look what it turns out to. Negative 15.876 is the lower interval, confidence interval, and 7.476 7.476 is the upper one. What number do we need to compare to see if it fits or not? 0, the hypothesized number of 0. 0 does fit. When you have one number's negative, one number's positive, this is an easy way to see if it fits or not. If they're both positive, 0's not fitting. If they're both negative, 0's not fitting. But if one negative, one's positive, 0's gonna fit. And when 0 fits between the interval, we cannot reject the null hypothesis. Do I have that on there? Where is it? Come on. Since the confidence interval includes the hypothesized 0 within the range, the null hypothesis cannot be rejected. There it is. Confidence interval. Okay, let's do p-value. Here it is. Equals t, dist. We calculated negative 1.66, but don't forget the rule for t, dist is you drop the negative. So we have positive 1.66, comma 4, degrees of freedom 4, comma 2, because it's two-tailed. So it says the p-value for the test statistics, negative 1.66 with 4 degrees of freedom equals 0.1723. Since 0.1723 is greater than 1%, way greater than 1%, the null hypothesis cannot be rejected. So whether we use critical value, which is on the PowerPoint, comparing this negative 1.66 that is inside the 4.604 plus and minus, whether we use confidence interval and we see that 0's between the two numbers, or we use p-value to see that 0.1723 is much larger than 1%. Whichever one we use, we cannot reject the null hypothesis in this case. Now, let me read your written assignment for the homework assignment. Before we go over another example, I want you to be able to relate it to this assignment. Here's week 9 instructions. There's a written part and Excel part. Let me say, the Excel spreadsheet is what you hand in. It has to be attached to an email, an Excel spreadsheet, not something else, not a picture of it, not a PDF. The Excel spreadsheet itself has to be attached when you hand this in. And then hand in your written part with it, all in one, please, if you can. This is due a week from today, 17th. Oh, St. Patty's Day. Oh, that's like a holiday. Oh, you gotta hand it in on a holiday. I'm sure you'll all do it before that day, though. Just checking. All right, so there's that, and then here's the homework. Which one is it right here? Here we go. I want to read number 2. Number 2, a computer firm wants to check whether the speed of a new processor exceeds that of an existing processor. So picture this now. This firm wants to see if a new processor will does it say exceed that of an existing processor. So they're probably going to collect the time it takes to do some process, do the same process on a computer with an old processor, put in the new processor, do the same process again, and time it, and see if it increases productivity or really decreases the time. Now it depends on which way they're subtracting. Old processor minus new processor speed, or new processor minus old processor. We'll read on and see which way. They measure the time required to complete 12 common tasks. There's our sample size. We're going to do it 12 times with the old processor and 12 tasks with the new processor, and see if these tasks can be done faster or not. So it says they'll measure the time required to complete 12 common tasks on 2 identical computers, one with the new processor, one with the existing processor. Okay? Consider the following hypothesis and accompanying results for a matched pair sample. Now I am not going to give it away and say for a matched paired sample on the quiz. Those words will not be there. You have to recognize it's a matched pair. If it's computer with the old processor and the exact same computer with the new processor, and it's doing the same task on each one, that's how you recognize it's a matched pair. Okay, even though it's not the same employee in this case, it's computers instead, it's the exact same task. Though there's 12 tasks, that's why the sample size is 12. The mean difference between the sample is negative 2.3. Where does it tell us which way they're subtracting though? Consider the following hypothesis accompanying results for the matched pair. Okay, it says right here. They measured the time required for the task with 2 identical computers. One with the new processor, X1, one with the existing processor, X2. For them to have, let's say this is increasing speed. You ready? this new processor is doing it faster. Let's say the old processor took 60 seconds. The new processor took 30 seconds. If I subtract the two, which way do I have to subtract them to get a negative mean difference? The new processor minus the old, or the old minus the new? Old minus the new, that'd be 60 seconds, old, minus 30 seconds would give you a positive. You're gonna do it the other way, it's 30 seconds minus 60 seconds will give you a negative. Notice that the mean difference is negative 2.3, whether that's minutes or seconds or whatever it is. It's probably the new time minus the old, because we're getting a negative there, which tells me that, let's think about this hypothesis. H sub O, the mean difference, and we're subtracting the new time, the new processor, minus the old, so 30 seconds minus 60 seconds, for example, and we're trying to prove that it takes less time with the new processor, so we're trying to prove that when you subtract the two, that it should be less than 0. So the alternative, H sub A, is that the mean difference is less than 0. The null is the opposite, greater than or equal to 0. It's a one-tail, because we're trying to prove that the new processor will exceed, or what's the word used here? Exceeds that of the existing processor. So the word exceed is what's telling us it's one way or the other. These are a little harder to determine if that alternative is a less than or a greater than or not equal to, because you really got to look into it to try to figure out which way is being subtracted here. The old minus the new, or the new minus the old? Go ahead.
So is it possible that even though we're testing, if it exceeds, that it actually takes more time, and then that's why it was negative?
That could be possible. You're saying that the new processor could take more time than the old?
Yeah.
That is possible. That's right. And then that would be a negative, subtracting old minus the new. That's possible too. There must be, here's the thing though, notice how it says 1 with the new processor, x1, 1 with the existing processor, x2. It's almost always x1 minus x2, but not always, not every single time. So you can't always make that assumption. I think we'll try to make it more clear on the quiz, which way to subtract. Let's look at the homework assignment real quick before we go on. Is it obvious which way this one's being subtracted? Hang on, which way, is this the homework? A computer firm, oh, this is the homework. Oh, God, we're giving away the homework? Shoot, let's look at, let's see with the first problem. It's not a story problem at all. Whoops. With the first problem on the homework, you're just given the numbers, not a story at all. Consider the following hypothesis accompanying results from a matched pair sample. The mean difference equal to 0. The alternative would be the mean difference not equal to 0. Now notice I used the word mean difference there instead of the symbol for mean difference. The symbol for mean with the D, I just put mean difference there instead. Mean 1 minus mean 2 is not supposed to be the correct way on these hypotheses, but I don't know. I feel like I should just go ahead and allow it. Who cares, right? Because in a way, you kind of can get the same result doing mean 1 minus mean 2, so I don't know, I can't say it's wrong. The mean difference between the samples is 3.3. It's just giving you the data, and then you're calculating it. It doesn't even ask you to do a sentence. But number 2, I want to bring it to your attention. I believe this one, it says, then give the final sentence explaining what it means. So you're not just reject or not reject on number 2, you're also giving the sentence of what it means to reject or not reject. Did the new computer processor exceed the processing speed of that of the old processor, or whatever it is you're trying to prove here? Your problem number 3 on your homework says to use the information from problem 2, but use the critical value approach. So you're using the confidence interval approach on number 2, the critical value approach on number 3, from the same information as number 2, so it's going to go fast because you're not going to have to calculate everything. And number 1 is probably p-value approach. There it is. Number 1 is p-value approach. So you got p-value approach on number 1, confidence interval on number 2, critical value on number 3. Is that right? Did I say that right? 2 is confidence interval, and 3 is critical value. Oh my God, this homework's not going to take an hour. Okay, we got another example. We have time? Here we go. We're going to 3.5, 10.5. Here we go. This is the one that I read to you to show you an example. A manager is interested in improving productivity at a plant, changing the layout. for each of 10 workers, she measures the time it takes to complete the task before the change of the layout and then again after the change. She calculates the following summary of statistics. That D with the line over it stands for the mean difference. Another symbol for mean difference. Mean difference equals 8.5. There's that. S with the D is the standard deviation of the difference. The standard deviation of the difference is 11.38. And then N stands for the sample size, number of pairs. There were 10 employees, I believe, right? Is that employees? Yeah, workers. 10 employees. Constructed 95% confidence interval. What's our significance, by the way? 5%, the opposite of 95, very good. Assuming the productivity variable before minus after. It's literally telling you what's going to be subtracted there to get the mean difference. Before minus after. So let's think about this. Are we trying to, okay, I want to make sure you understand the wording's kind of rough on this one. But if I go on to 10.6 and 10.7, you're going to realize it meant to say the researcher's trying to see if there'll be a change in productivity after changing the layout. Will there be a change or not a change? One tail or two tail? Two tail. Will there be a change or not a change? So, do we have the hypothesis on here? We don't, they're not showing us the hypothesis. Let's do the confidence interval, but where is, so, see that 2.262 for critical value? Let's figure out how they got it. Ready? Critical value, how did they get it? Equals T, I, N, V, parentheses. The significance you told me is 5%, but if it's one tail, we're supposed to double it. This you told me is two tail, because we're checking to see if it changed the productivity speed. Not whether we increased or decreased it, but changed it, even though it says improvement there. So in this case, we're sticking with our 5%, 0.05. Let me make that 0, comma. What's our degrees of freedom in this case?
9.
What is it?
9.
9. There were 10 workers, so you get subtract 1, 9. This is how we get, where is it? 2.262. Is that it right there? 2.262. 2.262 is our critical value. And so now we can set up the confidence interval. Here we go. 8.5. 8.5 plus and minus 2.262. 11.38. We're getting all this out of the story. 11.38 divided by the square root of the number of pairs of employees, which were 10 of them. We do all the math on that. We go 8.5 plus and minus 8.14. We get an interval of 0.36 is the lower one, 16.64. My question for you is, we reject or not reject? We reject why? 0 doesn't fit between them, so we have evidence to reject. Our lower one was 0.36, a positive number. Our upper one was 16.64. They're both positive. There's the example where 0 can't fit, when they're both positive or they're both negative. So we have evidence to reject. Let's put is there a sentence here? This represents a fairly wide interval caused by a high standard deviation. Wait, come on, tell us, where's the result here? Oh, it's on the next slide. Hang on. Let's get to the result, which is example 10.6. By the way, we just used confidence interval in this case. 10.6 says, use the information from 10.5. Can the manager conclude at 5% significance level if there is a change in productivity since they moved around the workstation with the new workstation? Here's your hypothesis. The mean difference equal to 0. The alternative is the mean difference not equal to 0. Says we found at 95% confidence interval that the mean different ranges are 0.36 all the way to 16.64, both positive numbers. Although the interval is very wide, the entire range is above the hypothesis value 0. 0 doesn't fit between the two numbers. Therefore, at 5% significance level, the sample data suggests that the mean difference differs from 0, that there is a difference. In other words, we rejected the null hypothesis. In other words, there has been a change in productivity due to the different layout of the workstation. We proved by changing the workstation that it changed productivity. As a matter of fact, it made productivity better. It had less time. Oh my gosh. I want to take the same exact problem. Let me go back up here. I want to look at those numbers. And I went ahead and said, okay, here's the confidence interval approach. but I wanna show you how to do it using p-value approach and critical value approach. Now let's remember the numbers. 8.5, I'll write them right here. 8.5, what's the standard deviation? 11.38. And the sample size is 10. So there's our key numbers right there. And what else did we calculate? We calculated, our critical T was 2.262. There's our critical T right there. So now, hang on, 10.5, this is 10.5, 10.6, 10.5, here we go. Critical value, let me make it bigger. Critical value approach, 8.5 is our numerator divided by 11.38 over the square root of 10 to get our test statistic T. Our test statistic T is 2.362. Here's our critical value. I want you to think of a number line. Think of a number line, plus and minus. Let me put plus and minus. 2.262. Think of where they are on the number line. Our test statistic is 2.362. Outside our critical value. It didn't land inside, just outside. Since it landed, since our test statistics outside that critical value, we have evidence to reject the null hypothesis. All right, now using p-value. Well, we have our test statistic now, 2.362. So equals T dist 2.362, comma 9 degrees of freedom because there's 10 pairs, comma 2 because it's a two-tail, equals 0.0425. What do we compare it with? Our significance of 5%. 0.0425 is less than 5%. It also gives us evidence to reject. Darn close to 5%. All of these were kind of close. But all three of them, whether we use confidence interval, critical value, or p-value, they all said we cannot reject the null hypothesis. Is that enough? Well, I have one more example if you need it. That's enough? All right, if anybody feels they need one more example though, 10.7, the next example down on this page, I posted all three ways of doing it. Let me get to 10.7 real quick. Let me just read it to you. Let's revisit the chapter's introductory case. Recall that the local ordinance required chain restaurants to post calorie information on their menus. This is all about, did people ingest less calories once they could see how many calories all the products were than before they did. Hey, before you pack up, I know some of you had me before, so you're gonna hear this again. But I have a note to myself that I wanna make sure that you realize this when it comes to real life, all right? When you graduate, you're gonna make more money you've made in your whole life. For most of you, it's gonna be more money you ever made in your whole life because, oh my God, you're making a salary. Oh, look how much money I'm making. Oh my God, this degree's paying off right away. And most of you, probably more than half, will usually figure out how to spend every penny of it. Every penny of it. But really what life's all about is how much you don't spend, all right? It's how much you save and not waste. You will have all these people that are getting laid off on government jobs right now, do you realize there's thousands of people getting laid off and they didn't see it coming. They kind of saw it coming, but they didn't think it would really happen, and it's really happening. And what companies do, because they know there's economic times get bad sometimes, is they have what's called retained earnings. It's where they saved some money and didn't give it to all the shareholders and put it aside, called retained earnings, in case we have bad economic times. One of the most famous retained earnings, by the way, is Apple. Apple has billions in retained earnings, and they're always gonna make it through rough times because they have this cushion that they develop. Well, that's what humans need to do. People make it through rough times, and we're possibly about to head into a recession because of all these tariffs. And if it happens, your parents and yourself and everybody's gonna realize what rough times really are. I mean, you guys, I don't know how old you were in 2009 when we got hit with a big recession. And it got rough for everybody in 2009. Were you guys too young to feel it?
I was 6.
You're 6? Oh man. Ask your parents, it got rough. Well, there's another one possibly coming. And the people who don't allow this to affect them are the ones who prepared for it by living under their means after they graduate from college. Focus on how do I live under my means? How do I put money aside? How do I then get into investing that money so the money can make money on money so I don't have to work so hard to make money? And you let it snowball. The hardest thing in your life, in my life to do, was that first $5,000. That was my goal when I graduated from college. I could not wait to save $5,000. What do I have to do to save $5,000? And it was the hardest money to save. But then I said, oh my God, I got my $5,000, I can pay off my student loans. And I didn't pay off my student loans, because I started realizing, wait, why should I pay this $5,000 towards my student loans? I'd worked it all the way down to $5,000, I have the $5,000 saved, when my student loans only at about 3%, and this money I have is making 6% right now. And it dawned on me, if I pay that off, I'm not making the 6% anymore, but I'm not paying 3% anymore, but if I keep it, it's like I'm making money on their money. And that's called leverage, and that's what companies do, make money off other people's money. And so I started saying, what else can I leverage? And that's when I started taking advantage of 0% credit cards. And 0% credit cards, and I take the money on these 0% credit cards and 0% cash advances, and I invest it, making 8, 9, 7% on the credit card money, and they're charging me 0%, as long as I'm making that minimum payment. That's called leverage. So the whole point of this whole story is, forget about the credit cards, because you gotta really be well organized to do that. But live under your means and save money, don't waste it. That's the point. All right, I'll see you on Wednesday.
If you didn't sign in, make sure you sign in.
Had Excel?